Assalamualaikum and very good morning. Okay, let us continue lecture for chapter 11, part 2. I really hope that you already watched the part 1. This is a continuous from there. Okay, so take a look in this example. This is a liquid level control system whereby the level itself, okay, this H is the level as a control variable. Okay, and then we have a level transmitter here, level controller, a transducer, and then our control valve here. Okay, and this is a manipulated variable. Okay. By looking at the instrumentation diagram, you can determine what is your manipulated variable. You can determine which stream should be the manipulated variable by looking at this control valve symbol. Okay, this is a symbol for control valve. Okay, so we have a level as a control variable. We have Q2 as a manipulated variable. Okay, and then we have Q1 as our disturbance variable. And we also have Q3 here. The question is, why Q3 is not a disturbance variable? Or can it be a disturbance variable? Just for you to think about it. Okay, let us continue. Okay, this is some assumption that related to this control system. The first one is a liquid density rho, and the cross-sectional area of the tank is constant. Okay, and the flow head relationship is linear. Okay, the level transmitter, which is TL, okay, IP transducer, IP, and a control valve. Okay, control valve has a negligible fast dynamic, only consists of steady state gain. What does it mean by this statement? This is the thing that I want you to understand. Okay, the dynamic of something, it's represented by a transfer function, which is k over tau s plus 1. If it is for transmitter, it should be km here, it should be tau m here. Same goes if you have a valve, tau vs plus 1, kv over tau vs plus 1. But in this statement, it has fast dynamic. What is fast dynamic? Fast dynamic means the value of tau, okay, for the Tm, for the Tv and Tip is very fast, meaning to say it's very small, approximately 0. And in this bracket only consists of steady state gain. Steady state gain is the value of k. Okay, so from this statement, straight away we can write the transfer function for Gm is Km, the Gv is Kv, the Gip is Kip. Okay, this is the definition. How do you interpret this sentence to get information about the transfer function? Okay, and then number 4, an electronic controller with input and output in percentage. Okay. When you have a process, the first thing to do is to develop the dynamic model of that process, so that from the dynamic model we can get the transfer function. Okay, so here we have an unsteady state mass balance for that process, and then the definition variable together with the information given, it just substitute directly. The question is how to get this equation. Okay, you have to visit chapter 2. Okay, but here I try to help you. Okay, so everything start with conservation of mass because it's only involve mass balance, which is the mass in and mass out. There's no energy here. So you should start with equation 2.6. Start with this one. Okay. The rate of mass accumulation, mass in minus mass out. Okay. And then from a physics, we learn about the density equal to mass over volume. Okay. So mass is equal to density times volume. And for this volume, we expand further. The volume is equal to cross-sectional area times level. Okay, so this is why we need to expand further because remember our control variable is a level. By equation, we want to find the relationship between the flow rate, the volumetric flow rate to the level. That's why we have to expand further to get this form because h is our control variable. And then we get this equation, this substitute. Okay, and then this information also given from the system, which is the density and the cross-sectional area is a constant. So we can take out these two terms. Okay, take out, come here, so that we have only the changes of level over time. Okay, the changes of our control variable over time, the changes of level over time. Okay, so this is an unsteady state mass balance. Remember that Q3 is equal to H over R. Okay, so we just substitute. And then to get a transfer function, before we get a transfer function, we should convert this equation into a derivation form. What is derivation form? Derivation form is basically the difference between current value and a steady state. And it's written in a derivation form, which is this symbol. Why? We should refer to chapter 2. Okay, I'm sorry, I'm not memorized everything, but maybe later on I will refer back. Why we need to put it in a derivation form. Okay, but here is showing you on how to get this dynamic model. Okay, so we continue by taking a Laplace into this dynamic model. Okay, just do the Laplace transform so that you will get a S domain. Previously, it is a T domain. Okay, T domain and S domain. Okay, so here you rearrange everything until you get this form. From this two, can you differentiate which one should be a GP, which one should be a GD? To determine that, you have to remember between Q1 and Q2, which one is your control variable, which one is your manipulated variable, which one is your disturbance variable. I believe this one is our disturbance variable. This one is our manipulated variable. Okay, so if this one is disturbance variable, so the transfer function should be GD and this one should be GD. And this one should be GP. It okay here because both GP and GD is the same. But there are also a case that GP is not equal to GD. But in this case, it is the same. Okay, and before I proceed to the next slide, I really hope that you don't have a problem to do a Laplace, okay, from here to here. Hopefully you don't have a problem to do that. Okay, so this is the transfer function. From a dynamic model, we get this transfer function, one for GP, one for GD, with K our remember that I did mention about Kp, which is a gain for the process, and then tau, which is a time constant for that process. Okay. Okay, so this is a standard form. It is an alternative form of standard, and this is for specific process. Okay. So we have a case here. Okay, we have a case of in this chapter, we're going to take a look about 3 cases. Okay, before that, let us go to my whiteboard. Before we proceed, I would like to write something to summarize for you so that you get the idea and don't get confused. Okay, so here we have a liquid level control system. Okay, liquid level control system whereby we're going to divide it into a set point change, and another one is a disturbance change. Remember, in process control, there are always only these two changes, whether set point change or disturbance change. But we have another variable here, which is we're going to see for the case of P mode, which is a proportional mode only have Kc. Same goes here. We're going to take care about the P mode, only have Kc. And another example about Pi mode, which is Kc 1 plus 1 over tau I s. Okay, so this is the 3 example that we're going to take a look, okay, on this liquid level control system, whereby it should start with remember the closed loop transfer function, which is y over y xp. Okay, and if you can memorize that, am gc gv gp 1 plus gm gc gv and gp. From this closed loop transfer function that you already derived from my previous video, we're going to go for this case. Okay, and here we have y over e, okay, with gd 1 plus e m gc dvg p. This is a general closed loop transfer function as you derived in previous video. But here we're going to apply these two into our liquid level control system. Okay, so we go back to the slide. Okay, this is our first example. Okay, remember our process here is a liquid level control system. Okay, this is the first case. Okay, which is we have a proportional control. The GC is equal to KC and we have a set point change. Okay, so from the closed loop transfer function, the general one that you already derived, so we're going to substitute the value of GC. Substitute it with KC. GV is equal to KV. GM is equal to KM. How do we know that? We have to go back to the previous one. Okay, this definition, like I said previously, the K, the transmitter, the control valve, and transducer only have the KM and KV. Okay. Okay, so this is the GP. We have to substitute here. This one, substitute here until you get this one. Okay. Substitute GC with KC. Substitute GV with KV. Substitute GP with this first order transfer function. This one and this one is KM in, is a KM. You have to write it. Make sure you have a pen and a paper. Okay. I try not to write it one by one so that I can make my videos shorter. Okay, if I write it one by one, it's going to be a long video. Okay, so substitute everything. Substitute GC with KC. Why only KC? Because we have only professional mode. Why GV equal to KM? You have to refer the given information previously. Why GP is here, is a first order, and then the rest also the same. Okay, substitute GC, substitute GV, GP, and GM until you get this equation. Okay, if you still didn't get this equation, you have to inform me. Okay, but you have to try it first. Okay, so when you have this equation, okay, when you have this equation, you have to substitute Y into H because of a level. Y is a general symbol. If you have a level, it should be H. If you have a temperature, it should be T. Okay, and etc. Okay, when you have this, you have to rearrange everything until you get this one. This is a simplified form. From this into this with this and this with KOL equal to this. I guess I really have to show it in my whiteboard. Okay, here is my whiteboard. Thank goodness that this whiteboard we can paste some equation. Okay, so that we don't have to go back to the slide each time. Okay, so we have here is a closed loop transfer function for set point change. Okay, it's a closed loop transfer function. Okay, closed loop transfer function for set point change. Okay, I don't like to write everything. Okay, you can write it by yourself. I just want to show you how. Okay, when we have this, we have to substitute. Okay, substitute Y in become H prime S together with H. Don't forget it is a set point. And then KM is still KM. GC we have to substitute with KC because professional mode. Okay, because of GC is equal to KC, it mentioned as a proportional controller. Okay, so proportional controller, so GC is equal to KC, and then we have GV is equal to KV, and then GP which is a transfer function for process, we have kp divided by tau s plus 1. Okay, same goes with the denominator. Okay, so gm is equal to km. I just put it in front. So gc is equal to kc, gv is equal to kv, and we have kp. The next thing to do is to simplify. Okay, we're going to simplify this equation. Okay, how do we do that? Before we simplify, we should write it in this form. Okay, remember last time when we do our mathematics, we're using a book that have a lot of line or blocks. Okay, but here we don't have it. I just want to write it in a form that you can differentiate the numerator and the denominator. Something like this. 1 plus km kc kv kp divided by tau s plus 1. Okay, so from here we're going to simplify. This is mathematics. Okay, this is not process control, it's just mathematics. So each of these should be timed with tau s plus 1. Why? Because we want to simplify. So it should be removing this km, kc, kv, and kp divided by 1 times this one is tau s plus 1 plus km, kc, kv, and kp. Okay, don't forget our left hand side. Okay, when we get this, the next thing is just rearrange kc, kv, kp, tau s plus km, kc, kv, and kp. To simplify further, take KOL as km, kc, kv, and kp. Okay, that's why we get KOL divided by tau s plus KOL plus 1. Now we want to change it so that it will be k over tau s plus 1. What we need to do is we have to divide everything with, okay, I continue here, h s plus h s SPS equal to KOL divided by 1 plus KOL tau S divided 1 over KOL plus 1. Okay, we really want to make sure it is in plus 1. Plus 1. K is K. Okay, that's why we get simplified into K equal to KOL over 1 plus KOL. Okay, or KOL plus 1, and the value of tau equal to tau divided by 1 plus KOL. So quite confusing, right? Not confusing, it's complicated. Okay, go back to the slide. And we get this. We put it as a K1 and tau 1. Okay. It is K1 and tau 1. Okay. Go back to the slide. Okay, so that is how we get this. Okay, how we get this tree from this. We have to simplify. You might asking me again, madam, why we really need to do this simplification? Because we want to get the final stage, which is this one. It is a first order transfer function. Okay, from this first order transfer function, which is we have closed loop transfer function for the system, and then we will start to introduce a set point. Okay, a set point change. Remember, last time you learned about several types of input. There are step input, ramp input, there are sinusoidal input. Each of it have their own transfer function. If you can remember, for step input, the transfer function is m over s. Okay, m over s. So by consider only step, because commonly is a step input. Okay, so this is a closed loop transfer function for set point change. Let's say the set point change is a step. Okay, change, how it's changed? It's a step change, it's a ramp change. Okay, but commonly is a step change. So we have to substitute this h into this. That's why we get this. Okay, and we get the final equation of a response. Then we have to come back. We have to convert back into time domain. This is, you can refer to table 3.1. I don't remember which number for this equation, but you will get this final equation. This final equation is actually the equation for the graph. Okay, the equation for the graph. Last time during a secondary, we learn a linear equation, we learn quadratic equation, and here we have exponential equation. From this equation, we can plot a graph by substitute the value of t. Okay, by substitute the value of t, we get this graph. However, because of this is a proportional mode, we get the graph with a offset. Okay, chapter 8, you learn proportional control only, you gotta have a offset. Here is the equation. On this equation represent this graph. Okay, but here we want to have this should be our set point. It's tend to be that it just here, so there are a offset. So in this chapter, you will also learn on how to calculate the offset. When we want a m as our set point, but it only managed to get km. The difference between am minus k1m is the set point. Okay, so I know you're still confusing right now, but let me finish first before we can refocus back on how what is the meaning of this set point. Okay, that is for the first case, which is we have professional control and set point. The same method is applied when you have a disturbance change. Okay, when you have a disturbance change and starting from y over d, gd, 1 plus km, kc, not k, sorry, it's g, gm, gc, gv, gp, starting from this equation, you have to substitute everything to get this equation. Same goes with simplification that I already shown you. And then again, you can calculate the offset. Okay, you can calculate the offset. Okay, we will focus on how to calculate this offset. And our third case is the PI control together with set point change. What differ from a previous one is the value of GC. Previous one for proportional control is only KC, but here we have a PI, so the GC equation, okay, the GC will be this one. It's more complicated, okay? And same, the rest is the same until you get a second order process. The closed loop transfer function itself is a second order. Compared to previously, it is a first order. This one is a second order. Okay, when you have a second order transfer function and then you introduce a set point change, not set point change, a unit change in a disturbance change, a step disturbance, you will get a damped oscillation. Okay, and then this is a table 3.1. That damped oscillation can be these two equations. It's quite complicated, and from the graph itself, it's going to be an oscillation and overshoot, and still a lot of which is covered in chapter 5. And also you can find the offset for this system. Okay, also to find the offset for this system. But for this PI mode, there is no offset because PI, the integral will eliminate the offset. Okay, this is mathematically showing you that there is no offset. Chapter 8, you learn about just a brief knowledge. If you have only P, you gotta have offset. And then for integral, it will eliminate your offset. But here in chapter 11, it's showing you by equation, by mathematical equation. Okay. Okay, now let us come back to our whiteboard so that we can see how to calculate the value of offset. Okay, so a simplification of this case, this is the first case, okay, case 1, okay, whereby it's a P controller and set point change. Okay, so when we have this, okay, we should have S HS over HSP equal to K1 divided by tau 1 plus 1. Okay, remember last time in chapter 5, you learned the dynamic behavior of first order or a second order. Okay, that is, you learn theoretically when you have first order and second order. In this form, okay, in this form is actually a first order. So when we have this first order process, we can predict the response. Okay, it should be something like this, right? There is no overshoot. Okay, for the first order process. For the second order process, yes, it does have a overshoot. Okay, what I want to tell here, when you have this kind of transfer function, okay, when you have this kind of transfer function, remember this is a set point change. Set point change is represented by this equation, which is this term. Okay, and as I said, the most common input is a step. Okay, input is a step input. So when we have a set point change, meaning to say we have step change of a set point. So this step input, okay, or step change in the set point was represented by m over s. Okay, this is chapter 5. When you have step input, it is m over s. Because of this case, we treat as a step change in input or step input. Oh, it's confusing, right? When we have an input, which is a step input, this is the equation that represent a step input. So this set point change is a step change. Okay, step change in set point. Okay, so when we have that, we have to substitute this into this equation. Okay, so we have h s equal to, okay, 1 tau I 1 tau 1 tau 1s plus 1 times m over s. Okay, so we have this equation of the response. A1 m s plus tau 1s plus 1. Okay, this is S domain. We have to convert back to T domain. Why we need to convert back to the T domain? Because this response is in T domain, which is here is a time, and here is the response at the H in T domain. Okay, so meaning to say from T domain, which is a dynamic model, we convert to S domain, in which is a transfer function, and we have to go back to the T domain to solve it. Okay, it start with dH over dt, then we convert it into a transfer function, and we have to convert back into a time domain, which is ht. Okay, so this Laplace is one of the method to solve this ordinary differential equation. This is ordinary differential equation. Okay, so you get what I mean, T domain and S domain, why we have to convert from T domain to S domain, and this time we have to convert back to T domain. because the dynamic model is an ordinary differential equation. What we want is the response. Okay, the response when we introduce any changes, whether set point change or disturbance change. The type of changes is the same as the type of input, which is can be step, can be a ramp or sinusoidal, or another type of input. Okay, so that is chapter 5 actually. Okay, we continue. So we want to solve this equation. Okay, we want to solve this so that we get h prime t and the equation. If you have this, okay, you can just straight away look at this table 3.1. Okay, let us zoom in. Okay, based on this equation, it should be about number here, number 13. Okay, when you have number 13, because here you have k 1m over s tau 1s plus 1. Okay, so equal to number 13. Straight away you get the t domain for this equation, for this Laplace. Okay, let us zoom out again. Okay, so we get k1m, so in a bracket 1 minus exponential t over tau. Okay, so this equation is the equation to get this line. If you substitute the value of time, t equal to 0, t equal to 1, t equal to 2, and then you start to get this graph. Okay. So process control is about a process. You have an input, you have a response. What happened here? Okay, last time in chapter 5, you just learned whether it is a first order or second order. Here is chapter 11. You have to simplify until you get first order or second order, and you have to solve so that you get the response. Okay, that is the function why we have to change from t domain to x domain. Okay, so now is for us to change, for us to calculate. Okay, for us to calculate the offset. Okay, so this is the equation. So this graph is represented by this equation. Okay, this graph is represented by this equation. This transfer function is represented by this. To find the offset, okay, to find the offset, okay, offset is a steady state error, meaning to say the response reach steady state. The response reach steady state, but it doesn't reach a set point that we want. It is below or higher than the value of set point that we want. Let's say we want it to be 400, it just may be 319, 318. Okay, so to calculate the offset, is basically we have to take the time that approximate to infinity, because in reality we are not sure at what time reach a steady state. Okay, so the best is we just take the time as infinity. And then we just substitute. Okay, the formula to calculate offset is basically H SP T prime, don't forget the prime, minus H T. So this one, so this is an S domain. Okay, in S domain. Or actually we can, which is the basically when you have this is the time domain, this is the S domain. Okay, so we just have M and then minus our this minus k1m. Remember that when we substitute the value of t to infinity, this term will be 0. So we're going to have only m minus kim. So this is the value of, and then in the lecture it continues as the m minus k1. K1 is equal to this KOL m divided by 1 plus KOL. Okay, and it's simplified again until you get m over 1 plus KOL.